So just imagine that there is a point charge, or any charge for that matter, or I mean a set of charge, a collection of charge whose center can be assumed as a point. And let us suppose that like you cannot see that probably. Wait, no, this is our point charge, and I'm writing this Q. Excuse me for my handwriting. Q, and there is a um, precisely cut seat in front of it, which extends up to infinity in both the directions. Uh, One might ask that what is the flux due to this point charge, the flux of electric field to be precise, of due to this point charge Q on this precisely cut surface. One way to do this is to find the actual distance and then do some symmetric trick to find the answer. That's not the aim of aim of this video, right? As you may know, let's find out how we can uh, generalize the concept and find the value of such a flux in general. So this is our surface, right? And this is the point charge Q. For that, let's move to Desmos. Before that, let me just clarify as to what we are going to do. So no, let's do that on Desmos. I mean, not Desmos, on 3D calculator stuff. So this is the 3D space, and I have introduced the point charge. I mean, imagine in your head that the point charge is at 0, 0, 0, which is origin of this uh, space, of this reference frame. I mean, I have introduced a circle, and excuse me, but this would be D. Where can I write D? Yeah, this would be D, right? So D, where D is the distance between the point charge and the plane, and the perpendicular distance to be precise. So as I vary D, I vary the distance between a particular plane and the point charge. For our sake of convenience, I have assumed that the D is 1. 1, wait, yes, 1. That yields us this nice looking sphere in 3 dimensions. Obviously, sphere means in 3 dimensions only, and it just barely touches this plane at this point, which is like 0, 0, 1, as can be seen from the intersection point of these two equations. I mean, if you solve them and neglect the imaginary part. Now comes uh, the specific slice that we're talking about, and since I cannot like draw the specific slice, I assume, I hope that you assume in your head that the point of intersection of these two curves with the green curve as the particular slice. So this is the slice that goes up to infinity, and again I want to repeat, my screen is not infinity, so you can't see them extend up to infinity, and the software has actually cut it in a precise manner, so it cannot move, it it cannot feel as if it's moving towards infinity. That's what's happening right now. So this is our slice, and our charge is right here. Now, coming back to the topic, like I think I've described the graph. Now coming back to the topic, let me erase this. So uh, the flux that passes through this infinite strip has to come from the electric field uh, that come out of this curve, this curve, right? Because uh, if the if if you consider a particular electric field line that comes out of like here or here or here or here, it will never uh, cross this strip, right? Like if it comes out of here, it will cross it somewhere here, which is not the considered strip. And if the field line comes out of here, it will never touch it or even cross it. So similar for this part, this part, and this part. So the only part that we are considering is this part. Wait, I have also drawn something for that matter. Why I'm not showing it? So it's the zoom out version of what I'm showing. This is the zoomed in version. So the electric fields that are passing through this curve are the electric field lines that would result in that would be needed in our calculation of flux through the surface that we're considering, and the strip that. And now if you see this curve, see this closed curve, closed 2D curve, closed 3D curve, I mean this part, I want you to just think of how that can yield us the uh, flux directly. Like directly, you don't need to calculate anything either. I mean, you just need to calculate this angle, and that's it. That's it. And what does this angle mean in real life? So what this angle means is when you uh, suppose the point charge is here, right? So when you draw a line from the edge of the strip from here to the charge, and then again same way you do on this side, you will end up with a V-shaped 2D shape. And the angle between that pair of line segments, like this will be one line segment, and this will be another line segment, and the angle between that line segment is the angle between these two planes. So yeah, this plane represents that. This two planes, the angle between these two planes represent that. And when you find that angle, you can just divide that angle by 2 pi and multiply the whole equation with the flux, the total flux through this sphere, and that would yield the flux through this infinite strip. Yeah, so that's basically it. I mean, it's a short video, it's a quick video, it's not a tough question. I mean, but I did not find it like in a book, in the standard book that we study in schools, though it's a school concept. Like if I mean, I wasn't taught this. Like, I would have been happier if someone would have come and said me this, like this when this concept can solve a lot of questions, right? Like you don't need to find uh, symmetry and all always, and it's like solving a pretty intimidating question just by some graph and all, like calculating a particular angle and set, done, that's it. So as I said in between the video,
I clearly did not explain as to why as to why taking that fraction and multiplying the whole flux through the sphere would yield such a result. And here I am trying to answer that. And so we need to find the flux through this curve to find the flux through that strip, right? So but it might feel disoriented at first. It feels to me, yeah. So this is the strip. So to find the flux through this strip, we need to find the flux through this part of the sphere. So to do that, I took the fraction and multiplied it with the whole uh, flux through the sphere, and here's why. So imagine you take a slice along this slice perpendicular to this intersection of these two these two planes. So you take that and you see from this angle. So you see it's an arc, right? And that arc is a part of a larger circle. So this arc contributes a particular segment of this whole circle, the circle that it intersects the sphere at. So, and if you think how much is that length, that length is actually the angle that is subtended in between these two planes, divided by 2 pi, the whole circle angle, the whole angle that is needed to complete a circle. So yeah, that is true for this particular plane. And similarly, if we change the value of um, the constant, and thereby changing the part where it intersects at, we can find it for we can have it here, or have it here, or have it here, or have it here. It really doesn't matter, because as you bring it closer to this edge, this though this curve, I mean this segment becomes smaller, so does the overall circle that it intersects at. So basically, the 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 segment that it uh, encloses in between these two planes, and the total perimeter that the circle has makes a, a particular constant ratio, and that ratio is true for any plane, right? So in general we can say that ratio uh, see, I mean, yeah, it's a feeling, right? I mean, it's not a feeling, that's the proof. I mean, it's true for all the planes, and therefore it's true for this whole curve. Yeah, so that's my proof. Peace out.